Theory part we have discussed. Let us take the data. Then this part also we discussed. This is also we discussed last time. And we discussed that we have taken a portfolio. And then we just use simple linear regression model to do the fit the capital asset pricing model using simple linear regression. And this is the estimate of alpha and beta. Okay. And this piece of code basically do a nice plot of. So this fitted line is the capital asset pricing model, and this green dashed line, that is a 95% confidence interval. So it basically tells us that if we expect on a given day that S&P 500 say goes up by 1%, then how much it can fluctuate. So this is the amount we can expect that it will fluctuate. So my IBM return can fluctuate between a little less than 0 to up to 2 point something. So the return could be anywhere between this range. So this is the idea. Now we are going to fit Bayesian CAPM, which is basically a Bayesian regression model. So what I have done, my main plan is to write a simple function later, so that basically RP is the sort of I could have used Y also, no problem. So I've taken ln RT, the log return of IBM. Here you can change log return of IBM to log return of Apple, or log return of like if you go up, you can either Apple, Microsoft, Intel, or log return of portfolio. Um, Here we have calculated the log return of portfolio. So you can plot the log return of the portfolio also. So you can take that. Here I'm just taking the size of the or the sample size. It will be 250, and then I'm creating the intercept and S&P 500. I'm putting it one matrix, so that will be my X matrix basically. So this is my X matrix. First column is all one, and the second column is log return of S&P 500. Okay, and then here I'm saying that prior mean of the log of the alphas and betas are 0 0. So uh, so prior mean of beta I have taken 0 0. You can take 0 1 also actually. So it's up to you. And then lambda 0 I have taken a diagonal basically diagonal matrix. That means elements are all 1, off diagonals are 0, and the diagonal elements are 1 and off diagonals are 0. And then A0 B0, this is the prior hyper prior of the gamma distribution, inverse gamma distribution, I think, right? I mean, if we go up, yeah. So here we are assuming inverse gamma A0 B0. This A0 B0 we have taken 0.1 0.1 kind of thing. So that kind of creates a flat, very weak flat prior with a very large variance. Then what we can do, we can just plug the values T transpose um, F transpose F, that is X transpose X basically. So we have kept it as F, but actually we can write it as X here. Actually we should have here, everywhere is Y is X transpose beta, so instead of F I should take capital X there. It will be my code and theory part will be notationally consistent. So I prefer, so let us take X here, and so this is X transpose X lambda naught, and then so yeah, X transpose X inverse, X transpose X plus lambda I inverse. Basically that is what we are trying to solve here. And beta pi is this. Here I have X here, so lambda 0 times beta 0, and that's it pretty much. So this is my posterior mean of beta. So I started with prime mean 0 0. My posterior mean alpha turns out to be 0.049 and posterior mean turns out to be 1.01. So my likelihood estimate, if you look at carefully, my likelihood estimate was negative 0.049 and 1.01. So that means this particular choice of prior, the effect of which is being washed out, because we have sample of size about 250. So which is, and that's why posterior mean is very close to likelihood estimates. So here in this piece of code, I just took the posterior mean and the likelihood estimates and print them, so that just to see a visual comparison. So this is posterior mean negative 0.04971 and this is negative 0.04989, and beta is 1.0118 and here 1.016. So posterior mean and likelihood estimates is very close to each other. So this is my analytic, this posterior mean is my analytical solution. Okay. Why I able to achieve this analytical solution? Because we had a conjugate prior structure. Because of the conjugate prior, we have a posterior mean. We know the exact posterior mean in mathematically closed form solution. Here, if we go up here, I know the posterior mean exactly closed form solution. And this is the rich solution for lambda I. Okay. All right. Next, it might happen that sometimes you mathematically, you know that posterior mean does exist, but analytical solution does not exist. For example, if you choose Laplace prior or double exponential prior, which is equivalent to L1 penalty, we know in that case the posterior mean is not, analytical solution of posterior mean does not exist. So in that case, we will be able to, what we have to do, we have to resort to some simulation study. That means some simulation technique or some numerical technique to estimate the posterior mean. So I'm just here trying to motivate you how we can think about obtaining a numerical solution of posterior mean vis-a-vis, as we, when we will not have an analytical solution, and most of the time we will see we will not have an analytical solution. So if we had to solve the same problem using simulation technique, right, what we will do, we have to simulate from the posterior. So what we can do, we have to first, so the strategy we can take, so this is my posterior distribution, beta naught, beta 1, beta k, given sigma square yx, follow a k-variate normal with beta, this is posterior mean and this is posterior covariance. and sigma squared follow given yx follow inverse gamma a in bn. Okay. Now what we can do, we can simulate first sigma I square. Suppose I'm in the ith iteration. This I stands for iteration. Suppose I'm at a ith iteration, sigma I will simulate sigma I square from the inverse gamma a in bn from this distribution. Then I plug that sigma I square here. Given sigma square, I'll check how I will try to simulate beta naught, beta 1, beta k from this conditional distribution. And this will give me this beta naught to beta k and sigma square together will coming from the joint distribution of beta and sigma square. Okay. So we will, this is the idea. So for that, I have to install this MVT norm package, which will help me to simulate from k-variate normal. Okay. All right. Let me just little bit explain, go slow here. So I have
So
put,
you explain again that like if we don't have an analytical posterior distribution,
no,
uh,
we will have a posterior distribution, but
but
suppose
we don't know the closed form,
we don't know the closed form. We also don't know the posterior mean.
right?
We
But
are, our goal is to estimate the posterior mean, right?
okay.
So how we estimate the posterior mean? We resort to the numerical solution. Now, what is posterior mean? Posterior mean is an integration. So basically it's average posterior mean. So what we can do, we can see if we can simulate from the posterior distribution some values and take the average of that, then we can say that okay,
What is
that
the closed form? How do we simulate from the posterior distribution?
that's a good question, and that is where a lot of techniques comes in, that we will not have, we will not know the posterior distribution. We will know the posterior distribution from only up to the kernel, and that is exactly the problem Metropolis Hastings faced, that they knew the distribution up to the kernel. And
So we have some information. We know the kernel then. Okay.
only kernel, we know the only kernel, we don't know the new normalizing constant and
Okay.
how to simulate from such distribution. Okay, and that is the problem they solved in the Manhattan project basically.
Oh, okay. Okay. Okay.
So in the physics the problem was they had to solve an integration problem.
Right. For some disintegration of atoms or something probably.
Yeah, eventually the problem boils down to they had to solve an integration problem.
Okay.
and
Okay.
and
Oh,
how they do
interesting. Yeah.
that,
Yeah. Yeah.
they have the way to do it is you think about a kernel. If you can the you can always write this integration into x into fx dx kind of form.
Right. Right. Right.
If you can write it that, then fx is your pdf, and if you can simulate values from the pdf density or that density function and take the sample average, and you, if you have enough computing power, you run the simulation long enough, then you hope that weak law of large number will kick in and the sample will mean will converge to the posterior mean. So that's how you estimate uh,
Ah, right.
the posterior mean, or the, in our case we are posterior mean, or whatever the integration, the value, the exact value of numerical solution of the integration.
So then, how do we get the values? Since we know the kernel, but we don't know the normalizing factor, how do we get the values?
That is exactly the problem they solve in Metropolis Hastings algorithm. That
Okay.
we will discuss in the coming lectures. It will take 4 or 5 lectures actually to explain you the all the things, all the nitty gritty.
Okay, okay. Yes,
Hmm?
sir. Thank you, sir.
Yeah. So I'm just giving you the motivation that why we want to solve this integration.
Yeah, yes, sir.
So far we are using only toy problem. Now we are going to a more and more complex problems where we will not have an analytical solution
But more realistic too.
realistic to the real life problem. We will not
Yes,
have
sir.
an analytical solution. And how can we solve this using uh, numerical solution? We need a numerical solution, and how can we solve it?
Sir,
Okay.
there would be some relation between the prior and the posterior, right? So if we sample the prior, we would get some relation for. I mean, I try to do
uh,
it myself. Actually.
Sir, also, if I remember correctly, in AML, you said that to solve such integration problems, there are two techniques, and you explained uh, one of the techniques. Was it related to this, or is that applicable here? I'm being very vague. Sorry, my memory is very bad.
um, So I don't know which technique, but definitely the most popular technique is for high dimension intake. See, okay, yeah. One technique is deterministic that typical numerical analysis uh, does. If you have taken any course in numerical analysis, that uses I think I can't remember like Simpson's one third rules and stuff like that. There are some formulas, but on those works only in the one dimension integration problem.
Oh, sir, I think Shailendra is talking about that autoencoders part where we had that variable, two types of autoencoders, but
Okay,
depending
variational inference. Okay,
yeah,
yeah.
variation inference and
Yeah, variational
Yes, sir. Yeah.
inference, yeah, is one technique. Yes, variational inference is one technique to solve integration problem. And another method is Metropolis Hastings or Markov chain Monte Carlo technique. So now I'm motivating you to Markov chain Monte Carlo technique. Okay.
yes, sir, yes, sir.
Okay,
And
sir. Okay.
variational inference is another technique which was used in the um, on the variational autoencoder. Yes.
Yes, sir.
Okay. All right. Yeah. So I'm now moving towards gradually towards Markov chain Monte Carlo. That will and full understanding of it will require 3 to 4 lectures, at least 3 to 4 lectures. But basically, I am now motivating you to just why we want to do these integrations. Okay.
So would we be covering that in the future?
What?
MC by any chance?
Yeah. In next 3 4 lectures, we will be covering that.
Oh,
I'm moving. That is what I'm trying to say. That I'm moving towards that. That I'm motivating you from to the towards Monte Carlo
yeah.
technique
The
and from
question that why we need it.
yeah, that is what I'm trying to explain you. That why we need that. That
Okay.
this discussion, this piece of code I written, but why I need this numerical solution.
Yes, sir. Understood, sir.
Okay. So, um, all right. So set dot seed, I put it as a one. You can took anything, but any Monte Carlo method is basically it will just flipping a coin and take a decision kind of thing. So if you don't put um, you know a seed, then your results and my results will be different. Effectively, it's like a password. But if you put a seed, then the results will be reproducible. With the, at the same time, you will enjoy all the advantages of Monte Carlo methods. So I here call the library mpt now, which I installed right just now. Now I'm for in first run, I'm going to simulate 30 values from these distribution, this posterior distribution, and I'm going to estimate the beta, alpha, betas, and the sigmas. Okay. Now there is something called burn-in. Burn-in, concept of burn-in, I will explain later when we will introduce the Markov chain Monte Carlo. For the time being, we don't need burn-in, so I have kept it 0. And if you look into the, just looking into the algorithm, you will get the, so this is burn-in, and then I'm just creating a sigma um, for a position for the basically a vector of simulation size and the beta of simulation size. Beta is a basically we'll have a k columns, and number of rows will be simulation size and all na values. And so if I just, and then column names will be all alpha, beta, whatever the names you are giving. Now the iteration starts. So I'm just saying that every 5,000 you just print the iteration number. Now I have to first simulate sigma square from inverse gamma. So what I'm doing here is I'm simply simulating from gamma and then taking 1 over. So that way by doing that, I'm just simulating from inverse gamma, sigma square, coming from 1 by gamma A and B. Now API and BPI is actually, this is where the posterior thing, yeah, I will give you the exact form in writing some places. And then once I get the sigma square, then sigma square times lambda inverse is the S. Then given the, and the beta pi also, we know that this is the posterior mean, this is the posterior covariance. I'm simulating the beta star from there. Once I get the, and then what I'm saying that if I is greater than burn-in, then you keep the value of sigma squared, sigma star in this sigma, this placeholder I created, and beta star in the placeholder beta dot draws I created. Now, by doing that, you can see the sense of the beta. Basically, first few draws, if I take 10 here, so the first 10 draws will not be stored. It will be unused. So typically, it is the period of um, we believe that it has not converged. By that, if you take I equal to 10, then we believe that by 10th iteration it will converge and it will go on. So we will only keep the observation after 10 onwards. So something, that is the idea of burn-in. In this case, since it is a direct, we know exact distribution and we know exact things, so we don't need issue, we don't have to face the issue of convergence here effectively in this case. So I just put burn-in 0. I mean, we don't need to throw away any data because we are not going to face any convergence issue. So let me draw that. So these are the first few draws. What I did first, I plot the alpha values over 30 draws. What are the alpha values that we got over 30 draws? And I just put them in. These are the alpha values over 30 draws, and I put them in, join them by the straight line. And then draw a simple kernel density plot that how these alpha values are behaving. So tends to be alpha values are like, slightly on the negative side. Now, these are the beta values over 30 draws, and I join them with a straight line, and this is the density plot, and these are the 30 simulated values of sigma, and I join them with the straight line. So these are the time series plot basically over the 30 iteration. So sometimes these plots on the left panel are called trace plot. Okay, and this is the, of course, the density of the marginal density plot estimated via kernel density in the of the alphas and betas and of the parameters. So more interesting will be if you run it in this way. So now it will be clear to you. You can see that these are the actual value of the alphas, and I join them with the straight line. So this is called trace plot. Okay. All right. Now I'm going to compute the posterior median, posterior mean, posterior standard deviation, and the 95% band, and posterior summary. I'm combine all these things as a posterior summary, and then I'm going to present this posterior summary. So this is the posterior median, this is the posterior mean. Okay, and these are the posterior confidence interval. Now if I run this, what I'm doing here, I'm just comparing the posterior mean analytical solution, posterior mean numerical solution. Also I'm writing the MLE. So posterior mean analytical solution is negative 0.049, and this is numerical turns out to be negative 0.048, and analytical solution is 1.011, and it is turns out to be 1.02516. Now what I will do is simple. I'm going to increase the simulation size from 30 to 3000. Okay, so it's done, and now I'm going to run the plot also. So this is the plot. You can see time series plot, and these plots, remember that these values are coming directly from the posterior distribution. If the values are coming from the posterior distribution, then trace plot will behaves like this. Okay, and the posterior median, posterior mean, median summary is this, like this. And now you can see posterior mean analytical is 4971, and this is 4949, and this is 1.01180, and this is 1.01664. So it is probably a little bit closer, but not still a bit far. So what we can do, I'm going to do, I'm going to simply increase it to 30,000 now.
So is there any way to tell uh,
So
about the convergence relation and the number of simulations required?
so once we have this thing, I'll tell you that. Now you can see that the actual value and the true value is very close to each other. The analytical value is my target value effectively.